Hello and welcome to this quick video on how to find the equation of the elastic curve for a beam with a discontinuous load. And by elastic curve, we're just talking about the deflection equation. You're going to see in different textbooks that deflection has three different variables that folks use. So there's either the italicized V, there's also capital delta, the triangle, or lowercase y. I'm going to go ahead and use the italicized V symbol, but I just wanted to clarify that in case you were used to seeing it as the capital delta or the y. And by discontinuous loading, what we're talking about is if we look at our beam, we have a uniform distributed load, but it doesn't run from A to B over the entire length. It's just over a length A when our entire beam actually has a length of 3A. You could be discontinuous with point loads because every time you hit a point load and you move on past it, you have a discontinuity in your loading. And you should already know from earlier strength of materials courses that you can integrate the moment expression. If you can write the equation of the moment, you can integrate that 2 times to get your actual equation of your elastic curve. And of course, one integral of that is the slope along the length of the beam. And so the first thing we need to talk about is how many moment equations are needed to describe this beam's moment. Take a second and think about that. And hopefully you came up with an answer of 2. You're going to have one that's valid from 0 to A, and then you're going to have a second one that would be valid from x equal to A to 3A. And I can show the 2 cuts there on the original beam. And so we want to write our moment expression. So let's go ahead and look at cut 1. We would start at one end of the beam. I prefer to start at the left end, and then you always want to stay with whatever end you started with. We would draw the forces that are acting. So we're going to have shear and moment, and we draw both of those in what is the positive nomenclature always. And this is only going to be valid from 0 to A for our values of x. And I'm going to go ahead and write out what the moments would be if we summed moments at the cut. Now, it might be tricky to see how we got the wx squared over 2. The 5wa x over 6, that's just the reaction that I'd already solved for you and we'd shown on the free body diagrams times the distance x to the cut. So I really recommend that you always take the time to draw the resultant, which would be Wx, and show how far that is from the cut. And of course, that's x over 2, so that's our Wx squared over 2. We can rewrite and solve that equation for m1, and then we can integrate it. So our slope is just going to be 1 over EI times the integral of our moment expression. And so we would end up plugging in our moment expression. And when we integrate that, we just get out our 1 over EI times our 5WA x squared over 12 minus now WX cubed over 6 plus our constant of integration. And then we go ahead and we can take the integral of the slope. But here we go. I do this all the time. We don't need to put the 1 over EI because it's already in the slope equation. So it's just the integral of the slope. And I'm just going to put the answer if we integrate our 5WAX squared over 12, etc. So we'd have 5WA cubed over 36 minus WX to the 4th over 24 plus C1X, and now plus C2. So we have this second constant of integration. So to find our constants of integration, we need to establish what our boundary conditions are. And boundary conditions are those values of either slope or deflection that we already know by default. For simply supported, we know at each end we have 0 deflection. So if we put in the value of deflection equals 0 at x equal to 0, we can plug that into our deflection equation that we just found, and we'd have 1 over EI. Oh, we're missing an x value there. All right, so I fixed that first term. I had actually made a mistake and I had just written a cubed. That should have been a times x cubed. And in fact, I'm glad that happened because you do always want to check your integration and you should always end up with the same amount of length terms. So a is a length term, x cubed is a length term, so I have 4. In the next term, wx to the 4th over 24, I have 4. And that's a great way to check that you didn't make a simple math error, which happens in these all the time. But back to plugging in our boundary conditions, I can now put in 0 for x cubed and 5wa over 36. So I'd have 1 over ei times 0 minus 0 plus c1 times 0, so 0 plus c2. So c2 obviously equals to 0. And then we might say, okay, well, we also know at the far end, at x equal to L or 3a, we know that we have 0 displacement, but V1 we said was only valid from 0 to a. And so an x value of 3a or L is not meaningful in that equation. And so we can't use that. So that means we don't know what C1 is. But we said we needed 2 moments to solve this. So let's go ahead and look at the second moment expression and see if that helps us out. Now this expression is valid from x equal to a to 3a, but we still must draw our beam starting at the same location we did on our first cut. This is critical. You know, when you draw a shear diagram, you start at one end and you add and subtract the loads as they come along, and then you draw your moment diagram by adding and subtracting the shears as you move along the length. You have to accumulate everything that's there to get a correct answer. And so we can quickly write our moment expression by summing moments at the cut again. And of course, we drew our moment and shear in the positive direction on the cut. But how did we get WA times X minus A over 2? I said earlier, I think it's really important you always draw the resultant, which is WA in this case. It acts at a distance A over 2 from the left end, so it must act at X minus A over 2 from the right end. So that's how we got that value. And then we can actually just simplify our formula, and because of the values that are in there, that actually simplifies to WA squared over 2 minus WAX. And notice 2 length terms, a squared and ax. So we've got some good math happening. So we can quickly integrate that term so that we can find the slope for our second range by taking the integral of our M2 expression. So we'll get back out 1 over EI times WA squared x over 2 minus WAX squared over 12 plus another constant of integration, which we better call C3 because that's a different one. And then if we integrate our slope expression, we're going to get back out a 1 over EI times the quantity of WA squared x squared over 4 minus WAX cubed over 36 plus C3 times x, and then another constant of integration, C4. So this is terrible because it didn't help us get C1 at all, and we just got 2 more constants of integration that we're going to need to use boundary conditions for to solve. Now, we're not even going to try to use the boundary condition of no displacement at x equal to 0, but we can at least now use that at x equal to L or 3a, we have no displacement. And that's just going to lead us to basically WA squared times 3a squared, right, over 4 minus WA 3a cubed over 36 plus 3a C3 plus C4. So still not really there yet. So what we need to do now, because now we're sitting with 3 unknowns, is we start moving into something called compatibility, and it's the compatibility of the equations. And so when we start looking at compatibility, we want to say, well, what do we know about the behavior that the first equation represents versus the behavior that the second equation represents? And really what we can say is that the slope at A from equation 1 should give us the same answer as the slope at A from equation 2, and we should get the same displacement from each one. Now, if you're not sure what that really looks like, come back over and look at the free body diagram. I've now drawn on the free body diagram the actual estimated deflected shape, so that's the black dashed line. And then I've also marked, so at A, I've drawn an arrow to show the height of the vertical displacement, and you can see there's no jump. It doesn't jump as I come from the left or the right, so I better get the same answer of what that displacement is, regardless of whether I come at it from cut 1 or cut 2. And then the same thing for the slope. The slope is just a value, and it's the same. It should be the same value. So that's really helpful because now we can plug in the numbers into our two equations for slope and set them equal to each other. Just plug in A, and we can plug in A to our two displacement equations and set those equal to each other. And when we've done that, we have a couple kind of ugly looking formulas, but we can reduce these some because each have some constants in it. But what we end up with is we're still now sitting with our three unknowns. But the nice thing is remember back at our boundary conditions for cut 2 and then our compatibility, we actually have three equations, which I've marked there. And there's the three unknowns, C1, C3, and C4. So you can either just solve them simultaneously using math methods that you learned back in high school. You can also set up a matrices and solve it with the matrix. But what you would get back out is that C3 is equal to negative 37 over 72 times WA cubed. Your C4 better have 4 length terms in it, and that's WA to the 4th over 24, and C1 is just minus 25 over 72 times WA cubed. Notice C1 and C3 are only in the slope equations. The slope equations only have 3 length terms, an x cubed or a squared x, whatever. But then we're really done. We could take the step to then go back and now write what is the slope equation for cut 1, and that's just going to be plugging in C1 into our slope equation. And then our displacement equation for 0 less than or equal to x less than or equal to a, we plug in our C1 because we knew C2 is equal to 0. And just to keep you honest, I'll let you go ahead and write out what the displacement equation and the deflection equation or the slope equation should be for the second cut from 0 less than or equal to x less than or equal to 3a, just by plugging in C3 and C4. So I hope that this video helped you understand how to do the equation of the elastic curve if you have discontinuous loading. If we had an additional point load at 2a from the left side, we'd basically have to make 3 cuts. We'd have 2 more compatibility equations that we'd have to write, and a much harder matrices to solve to find all of our unknowns or our constants of integration.